Hi, everybody. Welcome back to Astro Coffee Hangout. I know it's been a while. We have not done this in quite a bit of weeks or months even. But now we're back and we are doing a special one this week because let me just set the stage here a little bit. So last week I posted a Space Fan News on a news story that has been going through all of our feeds lately about how these neutron decay rates that scientists are measuring apparently have a discrepancy involved. Some neutrons that are at rest or in a container decay it into a proton and some other stuff at a rate that is slower, I believe, than the ones that are in a beam created by a nuclear fission reactor or something like that. They decay, like, I think the discrepancy is on order of 14 seconds. So scientists are having a real hard time reconciling what this decay rate discrepancy is all about. So I did a Space Fan News on this. Now, I admit that I base my stories a lot on other people's reporting. So I was reading other press releases and other stories about this experiment that other people had interpreted. I saw the paper that Dr. Broussard, Leah Broussard, who's at the the Oak Ridge Laboratory, whom my guest works with or is a colleague of, and is familiar with the experiment. But I got some things wrong on my interpretation, and so Joshua, my guest, reached out and agreed to do a hangout with me. So let me go ahead and introduce him now. My guest is Joshua Barrow. He is a PhD candidate at the University of Tennessee, but he is also a Department of Energy Program Fellow at where he is spending his time right now in Illinois at the Fermilab facility. So welcome, Joshua. Thanks for taking time out to be with us.
Thank you.
And so let's start a little bit with why don't you describe, if you can, the nature of the problem? I butchered it up in my little intro there. So why don't you give us a better intro into what the problem is, and then we'll talk about the experiment a little bit.
Okay. Maybe I should share my screen real quick.
Okay. When you do,
and look at some plots real quick.
Okay.
Just kind of
all right.
show everyone what the big deal is here.
Yeah. It's now showing.
Great. Okay. So basically, the neutron lifetime problem, which you just mentioned, is this seeming characteristic difference between what are called beam measurements and bottle measurements. What that basically means is that there are a collection of experiments, really just two, that are measured in a beam where we have what's called a thermal neutron beam produced at usually a nuclear reactor or a spallation source. Usually these take place at like the NIST facility outside of Washington, D.C., or also could take place in something like the spallation neutron source at Oak Ridge National Lab. And basically what they do is they measure what's called appearance. And what they really measure is the protons that come out of the beam when occasionally you have a neutron that decays. And so they count the number of protons. And when they count the number of protons and they do their math and they back out what happened before, how many neutrons there were and how many neutrons decayed out of their entire beam, they measure a lifetime, which is basically related to a half-life, if you will. And that time is 888 seconds, roughly.
Now, can we mention, before we get too far along in this, that a neutron by itself is not a very stable thing, is it?
No.
Go ahead.
It wants to decay.
Right.
So it's slightly heavier. And basically, if in nature, if there's a lower state that's possible, we always want to move to the lower state. That's a way of saying that entropy increases. Basically, the neutron is about 940 MeV, nearly a GeV in weight, and the proton is about 938. And so it's possible from basically electroweak physics, which is the physics of radioactivity, that there's a way out for the neutron to go to this lower state, which is the proton. And the way it does that is it decays by emitting an electron and a neutrino that conserves the leptonic flavor. and then also produces a proton so you conserve electric charge. And that's how neutrons decay. And basically, excuse me, that usually happens about every 15 minutes. So if you have a neutron, there's a very good probability, about 50%, that you would expect a neutron that you're just staring at to decay into a proton.
And how do you get the neutrons by themselves? How does that even happen?
So basically, in a nuclear reactor, this you get for free. There are neutrons that are running around everywhere because of fission, and just the kind of cascade that occurs in fission. And basically you just collect them with what are called beryllium reflectors usually. And beryllium has what's called a high cross section, which means that a low cross section. Forgive me, low cross section. So the neutrons bounce effectively; they don't get absorbed, and so you can actually create these mirrors that surround a nuclear reactor, and you can actually take those neutrons and you can bounce them around properly and into beams from that nuclear reactor and focus them just like you would light, which is kind of cool. The other method that is used, if not a nuclear reactor, especially because of nuclear proliferation concerns, we've moved mainly to what are called spallation sources. And what spallation is we take a linear accelerator, which takes a proton beam and accelerates it to several GeV, 1 GeV, 2 GeV, something like that. Very low energy in comparison to something like the LHC. And then you impinge those protons onto a target. So at the spallation neutron source in Oak Ridge, this target is mercury, actually, liquid mercury. And the mercury atoms, nuclei, I should say, they have this absorption of a proton and they basically break up. And when they break up, they produce about 20 neutrons. And those 20 neutrons have relatively high energy. They move out of the liquid, and then they can be what's called moderated. Similarly, as what would happen in a nuclear reactor, actually, nuclear reactors produce relatively high energy neutrons. They're moderated down by something that's very cold, usually something like liquid deuterium. And then those neutrons slow down onto speeds that are highly non-relativistic. Basically, you can outrun some of them sometimes. And then you can make beams out of these things in the same kind of beryllium reflector way. So that's our sources. That's how we get naked neutrons. And you can collect these in beams. You can collect these in bottles if you slow them down enough, where they basically are just, bouncing back and forth and just being affected by gravity. So you can trap them in bottles. And so the difference is basically here is that if you measure one, where you are measuring it in a beam, and you're measuring the number of protons, you're measuring an appearance of a proton. This is a highly non-relativistic process. Relativity doesn't matter at all, but we get a different measurement here if we measure it in a beam than if we measure it in a bottle. And basically this is the difference here is that in a beam we measure appearance of a proton, and in a bottle we measure disappearance of a neutron. So you know how many neutrons are in your bottle. You can count them, or you can expect what you pretty much know pretty well how many neutrons you start with, and you let them sit there for a while, and then you open up the bottle and you drop them all out, and then you count them directly. And then if you know what you started with and you know what you ended with, then you know how many of them decayed, and you can ascribe a decay time to that particular phenomenon. So that's kind of the major difference. But one of them is an appearance, one of them is a disappearance.
Okay, and I'm noticing that the error in the beam decay rate is a lot higher than the bottle one. And
yes,
is that because when you were describing the process of how you get these neutrons, it seems pretty complicated, and slowing them down, I still don't fully get how you're getting them, but I do understand that you there's a lot of processes here. What was the term you used? Spallation, or what was it
So
called?
you can, spallation is just
Spallation?
the production of neutrons from a target. So
Oh, that's
that's
just a production of them, and you
that's
get
just the
that in
production.
nuclear fission by splitting up uranium atoms, right?
You can think of it that way. It's a slightly different process, but you can think of it similarly.
Okay, so
The
we've
same
got
kind of
this.
fragmentation
We've
occurs.
got these neutrons that are coming out, and they are, it sounds like at first relativistic, but then you do something to them that slows them
They're not even
down.
relative. They're not even relativistic then, actually.
Okay. So
So
at any point, are they relativistic?
no, not really. So it
Okay.
depends on what you mean by relativistic.
Well, I mean that the effects of relativity would have an impact on time
They have no
dilation
impact.
and length
So
contraction, things like that.
if you look at the normal energy of a neutron produced in a nuclear reaction, uh, they're between usually 1 mega electron volt and 10 mega electron volts in kinetic energy. If you compare that kinetic energy to the mass of the neutron, which is right around a GeV, that's less than 1% of the total energy. And so that's in no way relativistic.
Okay. All right.
Usually when we talk about relativistic effects becoming important, where maybe for instance, like the proper time, for instance, would shift by 1 to 10% or something if you were between different observers, one being stationary in his own reference frame, and the other being relativistic according to this guy's reference frame. That would be, you would need about 100 MeV of kinetic energy for that to actually start being important.
Okay. All right.
And that doesn't happen.
Okay. Could I get you to maybe stop sharing your screen for a second?
Sure.
Yeah. Okay. Unfortunately, I don't have the control of that.
No, you're fine.
Good. Okay. Great. So all right. So you've set up the problem. You set up the problem, I think, quite nicely. Hopefully, I just turned up my mic, Uncle B. So hopefully, you can hear it. So let me just, because I hadn't done a Hangout in a while, I forgot to mention a few things. I am streaming on all the usual platforms: Twitch, Twitter, Facebook, and YouTube. I am looking at the live chats on all of those platforms. So if you have questions, comments for Josh, then let me know, and I will read them out, and we will talk about them when we go. So as we go along, and just wanted to mention that before I get too far along. Okay, so you've set the stage. We know now that when we have these neutrons, whether they're sitting in a container or whether they're grabbed from a beam, they are an unstable configuration as it is. Neutrons want to decay, and they want to turn into a proton and an electron and some other stuff. And but they're doing it at different times. And so what are the hypotheses about what's going on here before we talk about the experiment that Dr. Broussard has set up?
So the principal hypothesis is that someone did something wrong in their experiment.
Always the first question to raise, isn't it?
Yeah. So the thing that should be noted really is that there's really been only 1 or 2 real beam experiments. The beam experiment is incredibly difficult. It's hard to think about it this way. If you wanted to quantify the number of the number of molecules of water flowing through a river, okay, how would you do that? That's effectively what they have to do in the beam experiment. They have to know exactly how many neutrons are passing through their detector every second. And so it's incredibly difficult for that to count that.
Really? Because in a flow meter, like a river, you would have something that measures the flow rate of the water as it passes through. There's nothing analogous to that?
There is. The question is how accurate it is.
Oh, I see. Sure.
And then secondarily, the other thing is how do you measure the number of neutrons in a bottle before you actually measure them?
So, right, because the way you're getting the decay rate is you're counting the number of neutrons you have before and how many protons you find after.
Yeah. So the only way that we know really how to count neutrons is by having them absorb on what's called helium-3. And what that means is that you have this helium-3 nucleus, you have a neutron, it impinges on it, it creates some state, and then it creates byproducts that we can detect. That's really the only good way that we know to count neutrons. And we can't do that beforehand because we need to put the neutrons into the bottle. So we have a lot of modeling that goes into this that people are very confident of. And there's ways of also really extracting out other problems where we can really nail down how many neutrons are going through a beam or are being contained in a bottle initially. But that adds to the systematic error. That's right. The principal thing.
Okay.
So if someone got a systematic error wrong somewhere, then all of a sudden those error bars that you saw in
they were already quite large,
graph,
right?
And some of them are already quite large. They can change dramatically, and they can make things seem more consistent, perhaps.
Right.
That's probably not the case, and the reason that we say that's not is that because, if anything, the discrepancy is growing. And the discrepancy is growing in proportion to how much more precise and how much more quickly these bottle experiments are coming out. So there's a very particular experiment called UCN tau, which is ultra cold neutron tau, which is lifetime.
Mm-hmm.
And they were the green ones in that plot that I showed. And they're one of the most precise experiments that's occurred so far. And the thing that's really interesting about their experiment is that they actually have a bottle which the neutrons don't actually hit the walls. The neutrons are floating inside of a bottle.
Right, because one of the things you want to do is make sure that the container itself isn't affecting the decay rate results, right?
Yes,
so,
yes.
Okay.
And that's another, because there's absorptions on walls and so on and so forth. There are nice ways that people like Anatoly Serebrov have come up with to extract out, extrapolate away those collisions and absorptions on walls. But that still has a limited amount of uncertainty, or a finite amount of uncertainty that's important to characterize in your systematics. So the point is that there's all of these different experiments. They're doing different techniques, and all of the bottle ones really are agreeing, roughly. Now, they're not exactly agreeing. There's actually multiple experiments that Serebrov has done, for instance, in Russia, that are actually exclusive. So he measures it one way in 2006. He measures it another way in 2017, and they're actually different, and they're significantly different.
Was that the reference to the article that I read, and we'll get back to the reporting in a minute, but that said that it was actually making the problem worse when they try and reconcile these bottle decay rates, they do it again, and they get it actually makes things more confusing.
Sometimes, yeah. So the precision that some of these people are claiming in their experiments is low enough now that it's possible even to separate different techniques of bottles.
Okay.
So if you use a bottle which is it's a difficult thing to explain, but if you use a bottle that rotates, so like there's a bottle like this, right?
Yeah.
There's many different bottles that you can make. You could have this is a bottle, whatever. Well, depending on whether I turn this all the way over or just halfway over, or I come up with some way maybe of shrinking the bottle where I'm actually growing it and shrinking it, trying to extrapolate away these collision absorption effects on the wall. Or if I have a bottle that's magnetic and it's making these neutrons float on the surface and it's not actually contacting the surface of the wall at all of those techniques are actually producing different numbers.
Okay. So that goes to Adam Synergy's question then on how do you, what was it? Where to go? Darn it! How are you containing the neutrons in the bottle? Can they escape? And the answer
just
is
gravity. They're so slow. They've been made so cold. So to explain what I mean by cold and whatnot. So we have reactor neutrons. Okay, those are high energy, but they're not relativistic, as we discussed.
Right.
There's thermal neutrons. There's cold neutrons. There's very cold neutrons, and then there's ultra cold neutrons. Thermal neutrons basically are ambient temperature. So if you were to collect them in a gas, you were to measure the temperature of the gas, it would be roughly 300 degrees Kelvin.
Okay, room temperature.
Yeah. And those are moving at about 2,000 meters per second. If you go to cold neutrons, those are moving about 200 to 1,000 meters per second.
Wow.
And then there's very cold neutrons, which are about 50 meters per second. And then there's ultra cold neutrons, which are about 2 to 8 meters per second. And so ultra cold neutrons, you could literally outrun. They can bounce along a table and you could outrun or outwalk them. And because they have so low kinetic energies, when they're bouncing, the characteristic height that they're bouncing on the surface of the bottle or on the magnetic field that repels them because of their magnetic moment, they bounce very, very, very low. And so what that means is that gravity is enough actually to have a bottle that's big enough and it will never actually exit the bottle. That's basically how we contain them. You don't need to contain them really in a beam because they have enough forward-going momentum, kinetic energy, that you just basically run them through your detector and then have a big beam dump at the end and absorb all of them after you measure their characteristics.
And you got to account for that time, don't you? From when they were a beam down to when you've transitioned them to a bottle. I mean, we're only talking 15 minutes here, or 14 minutes. So the time it takes you to get all these neutrons situated
that doesn't matter actually.
Oh, it doesn't? How come? Because don't they?
Because the moderation. So you can take thermal neutrons. You can take reactor neutrons. So 1 mega electron volt or 10 mega electron volts. You can slow them down to ultra cold neutron temperatures of nano electron volts. Okay, nano electron volts in energy. So literally, 15 orders of magnitude in energy change. You can slow them down in a liquid deuterium moderator that's about that big.
Okay.
And they slow down very, very quickly. So they go from very, very hot to very, very cold very, very quickly.
Okay. Uncle B, I don't understand your comment on Discord. He goes, am I confusing units? He goes, GeV, giga electron volts, is 3 orders of magnitude greater than MEV, and I don't understand the context. Do you know what he might mean there?
So a giga electron, like the weight of the weight of a neutron is about 1 giga electron volt per c squared. Mm-hmm. We just say 1 GeV for short. And if you have an energy which is between, let's say, 1 and 10 mega electron volt, then that's about 0.1 to 1% of the total mass energy of the system. So it's not a relativistic thing because it's a factor of 1,000 different, factor of 100 different.
Oh, I see. He pointed out the context. He goes, you would need, when you said you would need about 100 mega electron volts, but he already said that they are working in the 1 to 2 gig electron volt range. So
no, so the the 1 to 2 GeV in energy that I was mentioning previously was the linear accelerator energies of proton beams used to impinge on spallation targets.
Okay.
So you need to have a relatively high energy proton beam hitting a basically standing still mercury atom. And it's only if you have the energies of those protons high enough that the mercury atom doesn't just simply absorb the proton and just kind of stick around. You have to hit it hard enough that it breaks up and then releases neutrons.
Okay, does that help, Uncle B? Thanks for clarifying that, Josh. I appreciate it. Okay, real quick question. I just did another SFN this week, just released it today, and it was all about the X-ray telescope that got launched by Russia and Germany. Why do you guys use electron volts as your main unit instead of masses and the other things that people think about, or wavelengths and frequencies?
So actually in neutron physics we do. In neutron physics we use lambda, we use angstroms all the time.
Okay, all right.
But they really are, I mean, they're all the same thing. They're just converting between the two of them.
Yeah, I know there is a nice relationship between energies and wavelengths with the Planck constant, but
The Broglie wavelength
E equals h nu, right? I think is the thing you use to convert from electron volts to frequency, and then you can go from frequency to wavelength
Sure.
with the speed of light. So okay, so I think we've done a good job setting up the problem and the science of this whole thing. Along comes Professor Broussard at the University of Tennessee, whom I think you work with. Am I right?
Uh-huh.
And so, and she proposes an experiment at the Oak Ridge National Laboratory because she has access to the stuff that can run this test. Can you explain the story behind the experiment, and then we'll talk about how the story, and maybe let's talk about the experiment first, and then what she's hoping to do with it, and then we'll talk about this parallel universe business, whatever that means. Okay.
Okay. So so dark matter has always been a problem, and
yes, it is a problem.
no one knows what dark matter is, and sometimes we can be developing different ideas in different contexts very independently, and then sometimes there are these little hints that occur that get certain people kind of excited that there might be a connection. And so one of the principal theories written down by a theorist named Zurab Errajani out of L'Aquila University in Italy was started in about 2001, and he had this idea which proceeded from Li and Yang in the 1950s, which is that maybe we could try and resymmetrize the standard model by making it a lot bigger. And by making it a lot bigger, we mean as big as like a supersymmetry sector or something like this. So he came up with the mirror matter sector, and he proposed that mirror matter was a good candidate for dark matter and could have some of the same kinds of needed astronomical observables, such as the halos.
So hang on, I want to make sure I understand this. So the standard model of physics is this idea that where we've organized and categorized all of these different particles that we know about. We've got protons, neutrons, electrons. They all exist in a category, and then we've got these other part of muons, quarks, and neutrinos. All of these different particles have been discovered in particle accelerators primarily, and then organized into this model of, well, gee, these are made of these particles, and when you do this to that particle, you get these particles. I know I'm butchering this, but I'm trying to make it really simple. And so the standard model is how you guys describe things, and when there are still spaces to be filled. Among them was the Higgs boson recently. There was a spot for the Higgs boson that, if it existed in the standard model, it should fit here, and we should see it at these energies, and it should take the following the following accelerator to show it to us. They built the LHC in part because they wanted to find this thing, and they did. And so there it is. The standard model is working. Things are fitting. But here comes this guy in the 50s. Well, I'm sorry, what was his name?
So there was Li and Yang.
Li and Yang.
They are probably, so Yang is probably the greatest living theoretical physicist currently alive.
Oh,
He's
wow. Okay.
Years old in China.
So this is just nobody we're talking about here. I don't recognize the name.
So basically they had this, they saw that in what are called weak interactions, or what we call weak interactions now, in the electroweak sector of the standard model, which is basically how neutrinos work. They saw that parity seemed to be maximally violated. And what that means is that we don't see any right-handed neutrinos. Okay, we only see left-handed neutrinos. So if you have a neutrino and it's moving, it's spinning only in a left-handed direction. Okay, and so it spins.
But your thumb is the axis of rotation, and your fingers.
So it's spinning. It's spinning this way.
Right.
We don't see any neutrinos spin this way. We see antineutrinos spin that way. That's fine, but we don't see any normal neutrinos spin that way. And what they proposed was that maybe so theorists always work from what are called symmetries. They like things to be nice and pretty.
We all like symmetry.
And so if you're just missing the whole right half, it's kind of like, what the heck? Okay. And so they propose that, well, maybe there's this entire other thing that is lying in a mirror that we can't access because it's sterile.
Okay, don't just say thing. This entire section of the standard model chart is like expanding the periodic table of the elements, only making a mirror version of it, right? I mean, it's like you really are proposing.
I have a good picture of this.
Okay,
actually.
Go ahead and share your screen, and I'll put it up.
Yeah, and it'll be good for this kind of discussion. So
Okay.
this is from Zurab. Baragiani. Basically, what Li and Yang saw as a possibility, they didn't write down the theory for it though, was that you could take what it's also weird to talk about this because in the 1950s, we really didn't have a conception of the standard model. We do now. So we're kind of recontextualizing what it is that they were doing.
I see.
But they basically they knew about most of these things over here, or some of them in some respect. And they said, well, why don't we just make everything prettier again and look at this other mirror copy, and then all of a sudden parity is better. Parity is conserved.
Yeah, but come on, all you did was just make that up. I mean, you just flipped it. And so, I mean,
you don't really know many theorists, do you?
No, I do, unfortunately. Yeah, no, I can't. But yeah, okay. So it was just an idea that maybe, what if we took what we know about particles and we made a mirror version of that?
And to be clear, this isn't a completely crazy tendency. So I don't know how much you know about supersymmetry, but supersymmetry kind of does something like this.
That's string theory, right? That's a string theory idea?
It leads to string theory.
Yeah,
it
that's
isn't
probably
string
why.
theory, though.
Yeah.
There is supersymmetric string theory.
Yeah.
But the point is that there are plenty of there's a bad tendency within particle physics that if we don't know what's happening, we propose a new particle or a slew of new particles, and all of our problems go away.
Yeah, but that's not always so crazy. I mean, Higgs did that, didn't he? So
yes,
it was crazy at the time.
And the weak interactions were proposed in very crazy ways. So it took a very smart person like Weinberg to realize that we need these like 3 extra particles, and then everything works. If you ever go and just read about the history of weak interactions, I mean, Weinberg just wrote something down that makes no sense, and it just works.
Okay.
So anyway,
so here we
go ahead.
I was just going to say, so here we have mirror matter, which is this. In part, it's an idea that helps to fill in the gaps for things that don't have parity, for things that don't have symmetry.
It would resymmetrize the total global model. That'd be the way that I would say it.
Okay.
Basically, if you only have one part, so just the standard model or just the mirror, they aren't symmetrized, but together they could be.
Okay. So we have this idea of mirror matter. What does this mean in real terms? What would this be? Another universe? Would this be a universe that has this stuff in it? Where would this mirror matter exist?
So I guess my question would be, is dark matter a separate universal entity? And I would say no. I think that if mirror matter is a dark matter candidate, and we're talking about dark matter has been a huge part of the development of our own universe, and it's inside our own.
Okay, could you stop sharing your screen for a sec?
Sure.
Yeah. So, okay, I got something to say about this. So, if you want, dark matter, I'm with you. Dark matter gives me grief in so many different ways, but it could be that first of all we know about it is that it has a gravitational influence on things that we can see. And that is all we know. And we kind of know where it is because we can kind of, where those influences are. Let me be careful. We know where those gravitational influences exist, and we can make what they call dark matter maps. But all they really are is a map of where the effects of dark matter lie. And that is it. That's all we know about dark matter. We can't see it, taste it, touch it, smell it, nothing. And so it's possible. Okay? It just is. I think this is a crazy idea, and I'm not saying it's true, but it could be in another universe. And the way in which it's interacting with ours is through gravity. But it doesn't exist in our universe any other way. How else can you explain something? I mean, every other particle in the world, in the universe we know about, we can detect in particle accelerators or see it in the universe. What kind of thing is completely unable to be interacted with in our normal baryonic matter universe? Seems really weird to me. Could be. So
and
all that's to say, it could
weird
be
to everyone.
Yeah.
So I guess the thing that I would always say is the most minimal assumption is that we're not actually talking about something that is entirely extra dimensional or extra universal or something like that.
With the mirrors, with the mirror matter stuff.
Or dark matter.
Or dark matter.
And I don't think that it takes a very large proposition to go the whole other parallel universe kind of thing, as just independent of mirror matter, but dark matter. I would always take the lesser assumption as
I would too. All I'm saying is that it's not so far-fetched, because this is some weird stuff. This is some weird, well, maybe it is far-fetched. I don't know. Hey, if you believe string theory, then anything's possible, because everything's possible and everything has happened. So, but don't get me started on that. Okay, so
and I would say as well that there are, I was reading an article from a couple of arguing professors on their blogs, and I think for Forbes or something recently, about how dark matter theory and so forth is a sham.
Yeah.
Most of the experiments are useless and whatever. And I think that in some respect that's true. But the problem kind of is that people are always interested in, we need to move on to the next thing. We need to come up with a better idea for testing things. And the problem kind of is that, okay, if you write down something that's interesting, maybe proposing like a brain world or something like this, it becomes very difficult to test. And so we're kind of, if we want to actually understand what it is, we have to test it. So we can only write down theories that we can test. Otherwise, they're kind of useless to us.
Right.
And so the way that I would contextualize the experiment that we're trying to do is, one, we're trying to understand whether or not there exists any kind of systematics that are unaccounted for in the neutron decay experiments, but primarily the beam experiments. But then secondarily, if we can show that there is an effect that exists that hasn't been properly characterized before, then maybe with some kind of interpretive structure, we can get an idea that maybe there's this new interaction that we haven't really seen before. And that would be something that would be very informative.
Right. Okay, good. Well, that's a good segue into this, because you brought up the symmetry idea, and then you introduced mirror matter and what it is. Now we're back to the experiment that Dr. Broussard and yourself are doing at the Oak Ridge lab. Briefly, can you explain it to us? What is the setup, and then what you're hoping to see?
So the initial experiments were planned for the high flux isotope reactor, which is a beamline that produces cold neutrons at the reactor, one of the more busy experimental regions of Oak Ridge. And the reactor was actually shut down for a period of time. It still is shut down. It's coming back online soon. And so we couldn't do that. So we actually moved to the spallation neutron source in a particular beam line there that we could get time on. And basically the idea is the following. We in the NIST experiments, where they measure the decay rate inside the neutron beam, the neutron passes through a very high magnetic field. And that magnetic field is high because you need to be able to capture the proton that results from the decay of the neutron in this particular volume. And basically, you have to make sure that this charged particle can then spiral around inside the magnetic field and be contained and then be measured. And so one of the hypotheses is that, well, maybe this magnetic field is leading to extraneous behavior that we don't entirely understand.
Oh, that's a good
And
idea.
so one of the things that we want to do at this first experiment is see whether or not there's any extraneous behavior. That's the first thing. If there is extraneous behavior, then we'll interpret it. If there isn't, then we'll kill some theories. But anyway, basically there's a large magnet that we're going to use that's about 5 Tesla. It's a little bit stronger than the magnetic field present at the NIST experiment, the beam experiment. And the neutrons will go through this high magnetic field region, and then they'll be absorbed. So the idea is if something weird happens because of this magnetic field, like you transition into a sterile state, an unobservable, invisible, dark state, then if you have a small probability of that happening inside the magnetic field, then you just keep going. You just keep moving. It doesn't, if you're sterile, if you've become sterile, then you don't interact with anything around us. And so what that means is that a small portion of the beam would theoretically have this extraneous behavior. And then the rest of the beam, 99.999 whatever percent, would just be absorbed in a beam stop, effectively, a trap. And that happens inside the magnetic field. And then the extraneous ones would just keep on going. And they have another small probability of what's called oscillating back. So they retransition into a normal state, observable state. And if you measure something on your detector, and we have a pretty accurate detector there, and we're not expecting anything because everything should have been absorbed by this big beam stop, then that's extraneous behavior. And it's extraneous behavior due to magnetic field interactions.
Okay.
And that might explain why it appears that there are differences in the bottle and beam lifetimes for neutrons, dependent on whether or not you're in a high magnetic field region or not.
Okay. Can I just try and restate what you just said to make sure I understand it and I'm getting it right?
Sure.
So the trick here is that what the goal of the experiment is to do is to try and get extraneous behavior that you're not necessarily accounting for in other beam experiments.
I would say to test whether extraneous behavior exists.
Okay, thank you. So to test whether extraneous behavior
Occurs.
exists, and if it does, then it's going to happen probably in the strong magnetic field that you've created that is designed to capture the proton once it's decayed. And by looking at, so most of these you can trap in a stop, right? Of
most of the neutrons.
Most of the neutrons you can, but the ones that have, okay, hang on. So the neutrons have gone through a stop and then decayed, right, into the magnetic field, or did they go through the magnetic field first?
So this is actually independent of decay. So the number of neutrons that actually decay in our experiment in the very short time that we observe them in flight is going to be so small that we don't care.
Oh, okay. So it's not about decay. It's not about decay. It's about whether or not there are extraneous behaviors which could lead to losses that would appear as decays in a normal lifetime experiment. That would be the way I would say it. And
So let's say this. If you're in a beam or a bottle experiment, and you have a systematic that you haven't accounted for that can lead to losses. Okay, what that would imply is that, well, you don't have as many neutrons in your beam as you think you do, or you don't have as many neutrons in your bottle as you think you do. And because those normalizations are different than what you think that you have, then you actually aren't really measuring the lifetime in a proper way.
Got it. Okay. And this would manifest itself in this experiment as a what was the word you used? A vibration or a
oscillation.
Oscillation.
That's that. Now, to be clear, that's an interpretation. So
this could happen.
Well, okay. Think of it this way: if you just want to run an experiment, you can just run an experiment. That is independent of an interpretation. If I run this particular experiment and I run neutrons through a high magnetic field region, and then I absorb all of them, supposedly, and then I don't see anything on my detector, well, then we would say that makes perfect sense. Okay, but if I observe that there are neutrons that come through somehow, that's also just a statement. The question is how you interpret either of those scenarios. And there are many different ways of interpreting the presence of neutrons that would exist possibly if this experiment, if it works out this way. If you have neutrons on this detector that seemed to come from nowhere because everything else should have been absorbed, then you start having to think about how could that occur. And one of the ways that could occur is what are called neutron to mirror neutron oscillations, which are a theoretical prediction of mirror matter models.
And that's where this whole thing got way out of hand, it sounds like to me. So all right, thank you. I think I understand it now, and I hope you guys do too. But let's get to this. What happened once word got out? First of all, how did this happen? Did Dr. Broussard publish a paper on archive.org, and then people just went nuts with it and made stuff up? I mean, what happened?
So there was a paper that we wrote, a white paper that mainly Leah wrote, Broussard, Dr. Broussard,
right,
with my professor Yuri Kameshkov, and who's at the University of Tennessee, and that was like in 2017. It was kind of our first expression of interest to do this experiment at HIFER. I've actually, I in the Google Drive, I did attach that paper. But if anyone is interested in these things, they can go and they can find my talks at the APS meetings.
Well, with your permission, I'll make that Google Drive public readable, and then people can download it, and I'll post the link in the description box of this video. But I can't do it without your permission. Okay. We'll do that.
Yeah, so and you can find these things on archive and so on and so forth. That's not a problem.
Yeah, but it's easier if it's all right there and they can just
basically the reason that this happened was we were approved very recently for this SNS experiment, and we have beam time coming up at the end of July and in the middle of August. So at the end of July we'll characterize the beam and understand how many neutrons there are passing through and whatever. And then in August, we will actually measure this with the magnetic field turned on and look for this extraneous behavior if it exists. And when that happened, when we were approved for this beam time, it's a pretty unique experiment. There aren't very many unique experiments at Oak Ridge, and I mean that with the greatest respect. They are a wonderful user facility, and they do great stuff for biologists and condensed matter physicists and helping them characterize the structure of their samples and so on and so forth with neutron scattering as basically a kind of microscopy. And but we wanted to use it kind of parasitically, and that doesn't always happen. And we kind of are getting kind of discretionary. We were getting kind of discretionary time for a long time, which basically means, hey, come in on my off day and we'll play around.
Yeah, Hubble Space Telescope has discretionary time as well. That's
okay.
The directive.
I don't know how that works,
well,
but
yeah, most viewers do. It's 20% of Hubble time is discretionary, and they can decide who gets it.
Okay, it's a lot less than that at Oak Ridge. It's a super oversubscribed facility,
right?
Because there's tons of people that want to do their work there. So when we actually applied to do an experiment and we got approval, that was kind of like, whoa, they actually want us to do something now, and they're giving us like a couple of days to do it. Like, that's insane. So when that happened, people started noticing, word got out. Leah and Yuri and Zurab and Klaus Kirch all kind of did little interviews here and there. And what ended up happening was that then there was this cascade of articles that really didn't cite. As far as I know, there was only one journalist, but this has appeared in probably 3 or 4 different like online settings, including like local news and so on and so forth, with no really citation backward about where it is that they got these things. And I don't want to speak for Yuri or Leah directly, but let's just say that I know them well enough that I'm pretty sure that I know they were being misinterpreted. And in some respect, it's kind of it's interesting because I went back over the last couple of days. I reread most of the articles, and if you read the first paragraph or two, it's this, very esoteric, very kind of, whoa, this is really cool, wild stuff. And then if you go and you actually read the rest of it, it becomes much more nuanced. So if you go beyond the first couple of paragraphs, they get taken more literally and seriously. But I think because it's kind of clickbaity, what ends up happening is that you shove all of this BS into the first paragraph or two that gets people excited, and some of us don't necessarily spend the rest of the time to go through it.
And that's just a sign of the times, isn't it? I mean, everybody's scrambling for attention, and so the first 2 paragraphs, the headlines, whatever it is going to be just absolutely outrageous. And then if you stick around long enough to learn the real thing, you might get a more accurate.
The other thing I would say is, and I said this in my YouTube comment, but so my professor is Russian, Zura Barozhany, who is the chief theorist behind this, along with people like Rubendra Mahapatra and Shmuel Nusanov and several other people who you can find on the archive. English is not a first language. And so when people kind of are speaking quickly and they're trying to get this just out as ideas, people kind of throw around this word like worlds or universes or parallel very kind of colloquially.
Right.
And we as experts kind of know what they mean, and we know that they don't really mean that. What they really mean is something called a sector. And the word sector is a very important one because it implies the possible existence of this other part of the whole standard model or the whole real model.
In this universe, it's important to also say that. In
this universe, yes. If the standard model is anything, it seems to be a nice, formulaic cookbook of everything that's possible at the microscopic level in this universe.
In this universe, yes.
But we know it's incomplete.
Right.
So if we add on other stuff, maybe we can predict new phenomena that would be occurring in this universe. But it just occurs in a different part of that formula. So for instance, we don't necessarily, we have sectors. Okay, we have the electromagnetic sector. We have the strong sector. We have the quark sector. We have the electroweak sector. So we have electrons and photons. We have quarks and gluons, and then we have neutrinos and leptons, and gauge bosons and other things. And all of these things are sectors, and they each have their own particle content. And basically, if we add some other sectors, maybe we can come up with phenomena that explain things that we don't understand if we only look at the standard model sectors. If we add these extensions, we might be able to get a better understanding of what's actually occurring.
And so this mirror thing would be an additional sector. It would be a
Yes.
mirror sector.
Yes.
But is it a mirror of the entire sum of all the other sectors, or is it just an additional sector on its own?
So one of the hypotheses of mirror matter, and this is why we call it mirror, is that there are what we say is that there are basically no new parameters. And what that means is that all of the laws, all of the mathematical laws that are written down for the known sectors are mirrored in the mirror sector. So all of the same formulas, basically the same particle content, but these two sectors don't talk to each other with anything except gravity, which makes it a good dark matter candidate.
You're right. That's right. That's a good connection because that's all we've got with dark matter.
Yeah. And so one of the other things that you might hear is that, dark matter isn't baryonic, or which I won't go into what that means, but there are all these kind of
baryonic matter is just all, protons, neutrons, electrons, all the stuff that we can
and
touch
what
and feel.
What it principally means is that there's a particular way that it clumps together, basically, because it's the fermion. So there are Fermi statistics and so on and so forth, Pauli exclusion principle, whatever, but don't worry about that. Those statements are generally only true if the other sector isn't sterile. If the other sector is sterile, all bets are off. We basically anything can be happening over there because there's no way that it affects in a large way our sector. So it's kind of completely independent. And some people might leap and say, oh, that's, it's a new universe or something. I don't leap that way, but, and there's also very particular, if it is mirror matter, if dark matter is mirror matter, that sector has a number of things that have to be working in a very particular way that are possible, even though they are symmetric between the two of them. That basically would, make it look like a very, very different place. Life wouldn't be there, etc. It wouldn't be a real universe kind of thing. Okay. So I'm being kind of hand wavy here. I'm sorry.
Well, sure, because this is just an interpretation. It's just an idea.
Yes.
And that's about all you can do at this point. But
yes, exactly.
what's your personal, you said you didn't quite leap that way. What's your personal opinion of this mirror sector then that would contain this other matter of the static?
So I'm technically an experimentalist. I don't do a lot of experiments, but I plan experiments and I do Monte Carlo.
Good for you.
But, experimentalists' jobs are to kill the dreams of theorists.
Yes, that's exactly right.
I
Observationalists in astronomy do the same thing.
Yeah, so I think that there's probably a 0.1 or a 1% chance that there's something there, that there's something behind these ideas.
Okay.
And that 1% chance, would be a very big deal. It would completely reorient the field. But I don't think that we're going to measure much of anything. I think we're going to be measuring a lot of zero. And the only reason I say that is because whenever you're dealing with these kind of beyond standard model things where we're hypothesizing about all of this other stuff, the number of hypotheses greatly outweigh the number of actually measured phenomena.
Exactly. Yeah.
And so statistically, you're kind of bound to fail. Occasionally it works out, and hopefully you have enough people in the community that can do a random walk, and then they kind of occasionally happen upon, they're like pigs finding truffles.
There's one.
Yeah. And so, our group is a bunch of pigs, and maybe we'll happen upon a truffle, but I don't think that we will.
Let's hope that quote doesn't get picked up.
But what I do think is useful, even if we measure zero, one with at least, so to be clear, and I want to be very clear on this, the thing that we're testing with the first experiment is just one interpretation and one model or kind of sub-model of the mirror matter hypothesis. There's a lot of other experiments that you'd have to do, and we plan to, to basically eliminate mirror matter as a theory. And this is just one part of that.
Got it.
And if we find this one thing, then it basically means that the other things would, from interpretation, be possible.
And a whole lot of other things would not be possible.
And a lot of other things would not be. But that again is an interpretation. Just because we measure extraneous behavior doesn't mean that we have the right interpretation.
Exactly. That's right.
So we would work that way. We would work to that, and there'd be a number of other experiments that we could do that then would point to that as the only interpretation that's viable.
Okay.
But that's a long way going. So it would take a long time to kill the whole theory.
Okay.
But it's possible to. And what we can, I think that the useful thing is even if we consistently measure zero, what we are doing effectively is probing a number of different kinds of interactions, which we really didn't talk about, but kind of the mathematical structure of the ways that these neutrons could do weird things, these interactions that happen with the magnetic field and other things. When we are looking for that kind of extraneous behavior, we write down those interactions and we can test those interactions. And if we know that those interactions don't exist, then that limits the ways that those interactions can be used in a broader context.
Yeah, I mean, this whole thing reminds me a lot of detecting dark matter. A lot of the dark matter detectors that are built use these giant tubes of xenon, and they expect that if dark matter is interpreted as being this one thing, then it should do these. We should see it as bright flashes in the xenon gas or whatever it is the experiment is deep underground. Usually they use neutrino type.
Xenon 1 ton or something like that.
Yeah, and so, but they don't detect anything. Doesn't mean dark matter isn't a thing. It just means that this interaction isn't what they thought. It isn't, at least not found in dark matter yet.
Yeah, so let me show one more thing here.
Okay.
I know that we're kind of running.
Yeah, we're running a little late, but this has been an important discussion, so I don't mind.
So I'll just show you this. So this is probably a plot that you've seen before. This is dark matter candidate mass, and then this is what's called cross section, which basically means the rate of reaction, the rate at which the probability at which the dark matter particle interacts. What they don't tell you when they make these kinds of exclusion plots, and basically what these exclusion plots mean is that like everything below these lines is eliminated. Like it can't exist. According to the Xenon collaboration and their experiment, you cannot have a particle that is dark matter in their detector that exists in this region inside the green line. That's what that means.
Right.
Every single line here, though, is theoretical interpretation. It's model dependent.
Yep.
So they're making assumptions about, okay, how many species of dark matter are you talking about? Are you assuming, everything is one particular candidate? Are you talking about particular spin statistics? All of these different things. And so that becomes very controversial because you have to remake those for everything.
Yeah. No, I get it. And that's one of the things about theories. I mean, you can come up with lots of reasonable ideas and then build an experiment to try and detect them, but if you get nothing, all you're doing is testing this one interaction with a theory that describes what it should be, and you haven't found it. It's a real quagmire. I mean, Einstein happened to get, I don't want to say he didn't get lucky because he was right, but I mean, so many of his things are only just now being experimentally verified. But for a long time, it was just a model. It was just an idea that needed to be tested. And so
there's like we kind of knew that gravitational waves had to be a thing.
Yeah, exactly.
But I mean, until we really measured them, it was kind of like, well, it probably is there, but we just don't know how to do it because it's too difficult of a measurement.
Right. Let me just get to something that Uncle B wants to get back to with we're talking about the proton beam. You still, when you were talking about the gig electron volt beam energies needed to get the protons or to get the neutrons stripped, you're still not talking about the velocity range of the beam neutrons. What is the velocity range of these beams?
So of a collimated neutron beam, a thermal neutron beam, which is usually the ones that people use, or cold neutron beam. Thermal neutrons are at 2,200 meters per second. That's how fast they're moving. They're not relativistic. And a cold neutron beam, which is even more useful for microscopy with neutrons, which is basically what people in condensed matter and biology want to do with them. They are about 1,000 meters per second.
Okay, there you go, Uncle B. I hope that helps because he's been thinking about this pretty hard since I did the SFN episode, and so he's been looking forward to this to get a lot of his questions answered. Let me just get to a couple comments. I know we're a little bit late, guys, but I want to read some of your comments. K Bear on YouTube is saying, if it's a candidate for dark matter, I think he means this interpretation, this mirror matter interpretation, then what is the explanation for it seeming to have so much more mass than the regular universe? Okay, we're in our universe. There's no other universe besides this one. So we should just get that straight. Sorry.
No, you're fine.
The hangout's supposed to be over. So we're not, forget that. Forget the universe thing. It's gone. We're not talking about that anymore. We're talking about interactions in our own universe. Mirror matter as a candidate for dark matter would necessarily be very massive, wouldn't it?
Well, so it depends on a few things. So there's something called co-baryogenesis. It's a very complicated idea. So you probably
have one of those. Sorry. I got one right here, man.
So there's an idea that basically is that one of the problems is how do you get so we know dark matter exists. The question is how does it develop from the Big Bang? So there's something called the inflaton field. I'm going to butcher this, but there's an idea that actually there were two inflatons, for lack of a better term. And what that means is that you can have effectively two little Big Bangs.
Oh no.
So what that means though is that you could have one Big Bang and then another Big Bang, and they basically start at the same time, but the rates of the decays of the inflaton field are different, and they produce different particles. And some of those particles would be our sector, and the other particles would be the dark matter sector. And so you create two sectors simultaneously, effectively. And because of this, their number densities can be different. They can have different interactions and so on and so forth. And basically, you can come up with a way of having dark matter be 5 times heavier than normal matter. That's an idea. Okay, it's highly theoretical.
Good. Because at the end of my hangout, you bring up this idea of two Big Bangs, and now I'm like, oh no.
Well, it's really one Big Bang. Think of it this. I mean, it's one Big Bang. Let me say it that way. But it's two inflaton fields. So
say it slowly.
Inflaton.
Inflaton.
Inflation.
Okay.
So inflation is what's important for making the universe relatively isotropic and homogeneous.
That's right. Yeah, and it's also in itself poorly understood. Yeah. Yep.
Yeah. So the hypothesis of people like Guth, I should say, is that you have this what's called a scalar field. It has a very particular form in its math, and this is what kind of started the whole thing. And then this field decays, and it becomes the particles that we know and love. but you can do that twice.
Mm-hmm.
That's the point.
Okay. All right. All right. I
It's
think
it's highly speculative.
yeah, I'm glad you pointed that out. Yeah, it's I think before we get too far down that road, we should probably stop because but I do feel like we've clarified the situation. We're not talking about other universes. We're talking about this thing called a sector, which might have it would be a mirror of the current standard model that would explain a lot of symmetries that do not currently exist, would fill in a lot of symmetries that we don't have, and these are all things that you can maybe study yourselves when you look up standard model and what it means, or talk with people that work with this stuff every day. But I'm glad we got this all settled. We're not talking about another universe. There isn't a mirror universe where everybody who's evil has goatees on it, or if you do have a goatee already, then you're going to get somebody without a goatee. It's nothing like that at all. It's just a way of filling in the standard model, and to test for it is this behavior of the neutrons and the interactions in the experiments that may be a bit anomalous, and they're trying to isolate if they can see some of this behavior in the experiment. When's the experiment occurring? This summer.
So we have beam time in late July.
Oh, okay.
What we'll do there is basically measure the neutron beam very carefully, and before we put in the extraneous element, the magnetic field, and then in mid-August we will test for the extraneous behavior. And so what we will do is we'll basically know what we expect on our detector without the magnetic field. That's the first measurement. And then we'll do the measurement with the magnetic field and see if we get something different on our detector.
Okay. Well, and any chance I can convince you? Then you got to process your data and stuff too, right? So when do you think you might have a result?
So I think the goal is that we would like to have this ready for a conference that's occurring in Madrid in October.
Oh, wow. Oh, that's pretty fast.
Well, it would be...
That's wishful thinking, isn't it?
Yeah, it would be highly preliminary.
Okay.
In principle, the data analysis is pretty simple because it's just a counting experiment. That's basic. It's just how many are you measuring? Mm-hmm. Are you measuring them in the proper... Is the distribution on your detector what you expect? That kind of stuff. The statistics of actually making limits where you're kind of trying to eliminate the theory where, okay, you can, so for instance, I don't know if you know this, but like the charge of the photon is technically measured not to be zero. Okay. The charge of the photon is measured as an upper limit of 10 to the negative 50 coulomb. Okay. Which basically is zero, by the way. But we never can measure zero.
Right.
But the statistics of actually getting that limit, that's tough. But we can present results that are preliminary, probably, that will hint at whether or not there's something there or there isn't something there.
Well, every experiment has noise, so that's why you can't get zero. So
yeah, and that's exactly.
All right. Well, Larry Keys wants me to ask you if you would, and I agree, and I was going to do this anyway. So many chance, maybe, I don't know, after this or maybe early next year, you might consider coming back and joining us about what you found.
Yeah. No, if we measure something, I think you won't be the first one. But sure. But if we don't measure something, I'll settle for this. This is perfectly fine.
Oh, good. Okay, great. Well, thank you. All right. Well, Josh. All right. Well, Josh Barrow, thank you for taking time out to talk with us. I hope this helps understand a little bit more about what's going on with this whole mirror matter and how it relates to dark matter and what the experiment is actually trying to do. And this is difficult stuff. This is nuclear physics, folks. So if you have other questions or comments, please leave them in the description box below or in the comment section below, and I will either forward them to Josh or try and answer them myself. So thank you so much for taking time out, Josh. This has been a lot of fun.
Yeah. No, thank you, and good luck with the channel, and I'll be sure to check back in.
Yeah, definitely, and thanks also for commenting on the original video. That really helped. So
Yeah, you have a lot of fans in our physics department, and they alerted me to the video.
Oh,
So
good. Well, that makes me feel good. All right.
yeah,
Well, okay. Well, thank you guys. And I'm sorry we went a little bit over, but thanks for hanging in there. And I want to thank all of you for watching. And as always, keep looking up.